So this is the first page of this part of the notes. So at the moment, so far we have understood how bonding forms. We solve this electronic part of the whole molecular problem. In particular, we used the H2 plus as a more detailed example, in which we also introduce LCAO-MO. So linear combination of atomic orbitals giving us molecular orbitals. Then we fill in this atomic molecular orbitals according to the Pauli exclusion principle. Thereby we can assess whether energy has been gained so that this molecule exists, is stable against being isolated atoms. So we are working under the assumption that the molecules exist. Okay, so in this picture, for the electronic part, we try different separations, and then we will find a bonding curve. That is, when we change the different separation between two nuclei, we usually find a curve with a minima. And we pick this minima, and then this is the equilibrium separation, and that will be the bond length. So today we will find some way connected to experimental method in which from which we can extract the bond length. And this depth is the energy gained, and that is the binding energy. Okay, so from now on, we will be focusing on this curve, and in particular, in the vicinity of the minimum of this binding curve. If everything stands still, the two atoms will be sitting right at R0. Okay? However, even from your first class in quantum mechanics, you know everything sitting still is something fishy. The position is known exactly, thereby there will be a lot of delta P, the uncertainty in momentum. Okay, so therefore, even without doing anything, you know that this equilibrium separation would there would be some even 0 degree. Quantum mechanically, there will be some 0 point vibration. That is the ground state of an oscillator around this minimum. Okay, so that is in fact true. In a way, you can look at this as a parabolic potential approximately, whereby the first thing you come to your mind is that this molecule, the two nuclei, will be vibrating about this minimum. It is an oscillator problem, okay? Earlier, I also introduced the idea that it is a three-dimensional problem, so that there's also a rotational part of the nuclear motion problem. Okay, so this is exactly what we are going to do. So let me go back to one page in the early part so that you know where we are. So this is something we discussed it about 1.5 weeks ago. So this is the scattering full Hamiltonian of a molecule. At that point, we said, now for simplicity reason, in order to handle it, we are freezing the motion of the nuclei so that we can treat this electron part first, okay? And then we went through many examples, LCAO, and then also introduced hybridization, sp2, sp3, etc. Okay, so now is the time to bring this term back to life. Ignoring this means ignoring the kinetic energy term of the nuclei, so they are frozen. Now I bring this back. Okay, so it is at this point, I bring back the nuclear motion kinetic energy term, and then this is the whole molecular hemitomia. All right, so this is where I copy this equation into the new part of the this part of the notes. So this is exactly that equation. And we make an approximation that the electronic degrees of freedom or the electrons' behavior can be decoupled from the nuclear part of the problem, so that the total molecular wave function is approximately the product of the electron wave function, which we already solved, LCAO, for example, and then multiply into a nuclear part. So far, we have not done anything about this nuclear part, and we are going to do it now. So the full molecular problem Schrödinger equation is, bring this term back, electronic part of the Hamiltonian, so this is the full Hamiltonian, the whole molecule's wave function equals the whole molecule's energy. Now this is the energy characterizing the whole molecule. So whenever we got some numbers, that signifies the molecule can take on that energy or the other number or the other number. It is about the whole molecule, okay? Not about the electrons only. We are going to do something including the nuclear motion. So this is nothing but H psi equals eigenvalue psi, all right? In blue, the part in blue has been treated, okay? So I highlighted that this electronic part operate on this electron wave function will give us the curve, the one that I just showed you, the curve times the electron wave function. So this part will not bother us anymore, all right? Now, immediately, because of this curve will go into this place when you operate on this part of the wave function. And this wave function, since this only operates on the nuclear positions, this part will move to outside the operator, and so canceling with this part, you will get a nuclear motion part of the Schrödinger equation. Okay, so this is what I did on this page, all right? So step by step, when I see this, I got the eigenvalue times the electronic part. But this thing we know, you give me a distance, it is one value. So this is this curve for different R's, okay? Then I see this electron part standing alone, I cancel it off, then I have a nuclear part of the Schrödinger equation, okay? In addition, the whole curve as a function of R is quite difficult to handle. To make life simpler for the nuclear to move in, we just look at the minimum, around the minimum here. So around the minimum, you see that it is like a parabola. Mathematically, you do the Taylor expansion, you pick up this constant, a number at the minimum, then the first order Taylor expansion is 0 because it is a minimum. The first derivative is 0. Then you pick up the second derivative. That means what is the curvature? You see the dotted line, what is the curvature here around the minimum, then multiplied with the second order deviation from the minimum, okay? Immediately you see this constant is not going to bother us, it's just a number, and then, but it will give us a number right here, okay? The value. And then this is half spring constant deviation in position square. So this is half kx square harmonic oscillator. All right. So that will be easy to handle. We can copy answer from harmonic oscillator problem. So that is the strategy. Moving on. Thereby, after doing all this, we will have this three-dimensional problem, okay? Meaning, we have two nuclei. We already invoked this relative motion. So this one is not going to move because relative motion already being done. So you will see the second nuclei connected with the one here with the bond, okay? Connected by the bond, that is the electron contribution. But now you will see that it is moving in a three-dimensional harmonic oscillator, okay? Meaning, radially, it will oscillate like that. And then in addition, there is a theta phi problem that has to do with the rotation problem, okay? So don't mistake this as a 1D harmonic oscillator problem. It is actually a 3D harmonic oscillator problem, okay? But this can be done. I think you might have done that last term. You have this central force problem. So this is central force. The harmonic oscillator only relate to the distance from the center, okay? So you can take this as the origin 0, 0, 0, you sit there, and then the other one will be deviation from the position, okay? So here you have this three-dimensional harmonic oscillator problem. This is the value that we are looking for. Here you see a constant. This constant comes from the Taylor expansion. You pick up the minimum value here. It's just a number. Read this number out. So this is the constant. Okay? Therefore, you look up what you learned last term about central force problem or spherically symmetrical potential energy problem. Okay? They mean the same thing. Immediately, you know the answer. Then, in a pictorial way, the answer amounts to the following coupled problems. It is a harmonic oscillator problem in the radial direction in R, okay? And then the theta phi problem as rotation. So this is a three-dimensional rotor problem. By that I mean the distance is fixed, but this n can live anywhere on the surface of a sphere, okay? I think you should have done that, but the answer is very simple. The solution is YLM theta phi. The harmonic, the spherical harmonics. Okay, so suddenly we know the solutions, the components of the solutions. The radial part, you can copy out the oscillator wave function. Then the theta phi part corresponds to the spherical harmonics, the orbital angular momentum. So without doing much new mathematics, because that decomposed into two problems of which we know the solution. That is the lovely thing, okay? So the nuclear wave function suddenly can be written down. Well, apart from a normalization, okay? But if you normalize everything by itself properly, the whole thing will be normalized. The nuclear wave function, diatomic molecules here only, okay, is rather simple. there is a part has to do with harmonic oscillator solution. That is the radial direction along R, going in and out. There's a minimum there, going in and out, okay? So this is a typical QM problem. And then you can look up the solutions. Of course, you know there is a quantum number n labeling the harmonic oscillator states, right? This n is the one that goes with the harmonic oscillator allowed energy, the quantum number small n, all right? Well, I think you all know this. So that is the oscillator part. The theta phi part, the rotation part, if you remember, the story goes, when you do a three-dimensional central force problem, you will bring up a term that has to do with the centrifugal force, right? Even classical mechanics, you see this. All right? In the radial equation. So this is the orbital angular momentum square. When you see this in quantum mechanics, you already know the eigenvalue and the eigenfunction, because YLM theta phi are eigenfunctions of this L square operator, with the eigenvalue being L times L plus 1 H bar square. Okay? So we don't need to do anything new, but we already solved the problem. Okay? So all of a sudden, without doing any new mathematics, when we observe this part of the nuclear motion Hamiltonian, we understand that we can solve it without any effort. So the eigenvalues corresponding to this eigenfunction of the nuclear motion is the harmonic oscillator eigenvalue, okay, plus, because there is a vibrational energy, add to a rotational energy. The rotational energy will be L square. Well, this is YLM theta phi is the eigenvalue eigenfunction to L square over 2 moment of inertia, 2I, okay, 2 mu R0 square. So without doing anything, we solved the nuclear part. We have this H nuclear wave function equals the eigenvalue add together, the nuclear wave function. Okay? Now, if you're not happy about this without math treatment, I encourage you to, now, step by step, plug this thing into here and then see how this operator, the Laplacian, you write it out in R theta phi and then operate this product of wave function through, okay? This is separation of variables. The wave function will multiply where the eigenvalues will add. That is the spirit of separation of variables. So we have used that here, okay? So nonetheless, we solved the problem, okay? So let me summarize. We are done. The rest are the consequences, okay? So the electron, we solved it in the past 2 weeks. They provide the bonding. The bonding here is now represented by this curve. Then we focus on the around the minimum, thereby we need this number. Okay, the first thing about the bonding. Secondly, the electron provides this curve, therefore the electrons are responsible for providing this curvature. Okay, therefore they are responsible for providing the bond strength, the spring constant. The curvature is the spring constant. So the electrons are doing things, although the discussion are focusing on the nuclear motion. The electrons are responsible for giving us the bond about which the nuclei oscillate and rotate. All right, so they are there. Okay, they don't disappear, they are there. Okay, without them, we don't have this part to discuss. For the nuclei, there is a harmonic oscillator motion like this. Okay, that is exaggerated. It should be around this minimum. Okay, something like that. Okay, and that will give us a radial part harmonic oscillator wave function. Around this rim of the minimum, but it is 3D, you can imagine there are rotations. Okay, and that will give us the YLM theta phi with the eigenvalue L square, L times L plus 1 H bar square, that is the L square eigenvalue, divided by 2 times, this is the moment of inertia, mass times the distance square. Okay, now we are done. Okay, so let's look at the whole solution. So this is the analogy. I copied another old page out just to remind you that I already gave you the big picture at the beginning, and now we are zooming into that part of the big picture. So I have discussed this previously, okay? So that is what we just did. So putting all the things together, this is the punchline. Okay? The electrons here give us a constant, the minimum, as well as this omega, which is the curvature. Okay? Then the nuclear motion will contribute this radial harmonic oscillator type eigenvalue, as well as the rotational motion give us this orbital angular momentum, the rotor type eigenvalue. So in order to describe, now listen carefully, in order to describe the total allowed energy of a molecule, there are these 3 terms. Okay, now this is where we discuss the nuclear motion. So that brings down this brings out the minimum number. So here, just a number here, all right? And then we have to address for the nuclear motion, which vibrational quantum number it is in. That is to say, is it vibrating just slightly, or it is vibrating more rigorously? Slightly smaller quantum number, energy will be lower. More rigorously, the quantum number n will be higher. Do you understand? And then we have to discuss whether it's rotating rather rapidly or rotating just leisurely. That has to do with the quantum number L. All right? So, in order to address the energy of the whole molecule, we have to do something like this. We have to tell clearly which electronic state, but that is usually just the minimum. Okay, so a number, and then we have to address which n quantum number it is in, and which L quantum number it is in. Vibrational, rotational. Okay, the analogy is like sending a letter. You have to write down in the address Hong Kong Island, Kowloon, New Territories. Okay, so you have to say which which minimum it is in, okay? For example, there may be electronic excitation. There may be a curve up there, or although ground state not occupied, okay? But that is not our focus. We will not discuss this electronic transition. We will discuss rotational, vibrational transition later. The second thing is that it's like, after you say it is new territory, you still need to say SHA team, okay? And then you say Department of Physics, CUHK, okay? Therefore, fully address a place, you need several things. Fully address the energy of a molecule, you need to tell us what is this term, what is the vibrational state, what is the rotational state, okay? One big reminder. Actually, we have YLM theta phi. For the rotational part. But the rotational energy depends only on L. Therefore, after you indicate what is L, there is some intrinsic degeneracy. There is a M quantum number behind the YLM that can take on 2L plus 1 values, okay? So if you tell me L is 2, actually there are 5 states hidden behind this energy, degeneracy. For M can be 2, 1, 0, minus 1, minus 2, okay? So that's why I wrote down degeneracy behind M. That is what I meant by that, okay? So this is the whole story of addressing the energy of a molecule. So up to here, any question up to here? We are done with the big picture. Is that okay? Any question? The remaining 30 pages or so want to develop this answer or apply this answer. Okay, if not, then the second concept is to look at the energy scales. Typically, what is this? Typically, what is this? In particular, what is this? Because that will set H bar omega, will set the separation between vibrational level, okay? And then what is H bar squared divided by 2I? This is the moment of inertia, okay? That will set the typical energy of the rotational level. All right, so you understand the question? The next question, okay? We want to know what is the ballpark value of this number, this energy, and that energy, all right? Now, for those who don't want to know the details, you ought to know the answer. Let me first tell you the answer. Now, this is easy. Basically, this is the binding energy value, okay? So as introduced very early on in the last part, this kind of binding energy thing is about a few electron volt, okay? 5 electron volt, 7 electron volt, well, that is about the right ballpark. So the first term is several EV. I'm advertising the key answer, the key result, okay? But that is the most important thing. Then, what is the vibrational thing? We will see that it is 1% of the first term. Well, that is roughly, okay? So that will be 0.1 EV to 0.01 EV. I mean, this is 1% of this term. okay, about that. And then the final term is, the question is, what is the typical value of h bar squared divided by 2i? Okay, then let me tell you the answer. It is 1% of the second term. Okay, so the first one, 7 eV, 8 eV. The second one, 1% of the first one. The third one, 1% of the second one. So it is 1% times 1% of the first one. Okay, so that will be 0.001 to 0.0001 eV. Okay, now, if you don't want to know anything, keep this in mind. Okay, now, the first one, several eV, is at the limit of visible. We can see something like up to 3 eV, starting from 1.4 eV or so. That is our narrow range of vision. If you have 5 eV, it's ultraviolet, you cannot see it. Okay, so that is ultraviolet, sometimes may be close to our limit of visible range. Okay, UV is safe. 1% of which is 0.1 eV to 0.01 eV. 0.01 eV is something that you will feel warm. You cannot see it, you can feel it warm. Okay, so that is infrared. All right, so the vibration has to do with infrared. Get me? The third term is 1% of the second one. It is 0.001 to 0.0001 eV. That is far infrared to microwave. Okay, that is the rotational term. Okay, all in all, keep this common sense in mind. And now I'm going to introduce a rough estimate of this number. So the first thing already introduced. So what is this? Or even if you want to go to the second curve, you may ask, what is this? Okay. But if you think about what is the binding energy, it is easy to get that. Okay. It is a few electron volt. You can even estimate by some quantum confinement method. By quantum confinement, we mean the following thing, right? Why are the two atoms bind together to form a molecule? Because there is a bonding, okay? And now after all the work, we know that the equilibrium separation is R0. So this parabola is trying to confine the motion in the vicinity here, okay? So thereby, by a particle in a box, you know the typical energy will be of the form h bar square divided by the mass, and then the separation, the distance square. Okay, this is how we confine the atom. You plug in reasonable numbers. This is 1, 2, 3 angstrom, the equilibrium separation of many molecules, and therefore you will find that this ratio, h bar square divided by a mass of a typical atom, and then the radius, the separation square is about a few electron volt. As advertised, we can only see up to 3 eV. So if you have 5 eV, it is in the ultraviolet range, usually above what we can see. That's the point. Okay. The second thing is about vibrational part of the problem. So we want to have an estimation of this h bar omega. That is what we want to do. Okay. So here we use a very rough estimation. We can think about it, okay, this binding energy depth, we already know it is estimated to be something like that, and that is a few electron volt. Okay, that's what we're trying to do here. Okay, so we can think that we have a spring constant which is unknown. We want to find this. Okay, we compress or stretch the spring from here out to here. We are climbing up this curve, the harmonic oscillator curve. If we compress by this amount R0, okay, or half of it, it doesn't matter, okay, then we will get this kind of energy. We are climbing up the curve, okay, so we are climbing up this amount when we compress it by R0. So we have this rough estimate. The spring constant times R0 square will give us a few electron volt, which is given by this, okay? And now, this spring constant is the reduced mass omega square, okay? We want to find spring constant or omega, then we know the h bar omega. That's the strategy, okay? And this is the reduced mass, and therefore it is much lighter than the mass of an electron, the m. This is mu, okay? The electron part, LCAO, will give us the binding energy, so we are confining the electron here, the m. Thereby, we can use this equation, plug in the K, plug in this, and then we can solve for omega. All right, now you solve for omega, you get an expression like that. Then you see a combination called 1 over mu m, multiply into something that we know. Okay, well, by that I mean we have this part, okay? So we can multiply, divide the m here, so that I have to multiply m square here. So I have this ratio multiply into a few electron volt. So the end result is the vibrational, the spring constant, the typical h bar omega is this ratio, the square root of an electron mass over the reduced mass. Now this is atoms mass. This is electron mass. This is at least 2,000 times, but could be 10,000 times or more, because hydrogen is 2,000 times, but other molecules will be you have a much bigger reduced mass from the nuclei than the electron, okay? So all in all, you will have this being a small number, and 1% is a good estimate. This term already estimate that is the binding energy, several eV. So the answer is h bar omega is 1% of the binding energy, okay? So we have that, and that is in the infrared. The rotational, we aim at getting this typical energy. We know that it is governed by h bar square over 2 moments of inertia. All right, so we write it out. And then again, if we multiply an electron mass here, we have to cancel it off, multiply up there. So suddenly we have the answer. This is the electron mass over the reduced mass, the two big atoms heavier, 10,000 times heavier at least. So this will be easily 10 to the minus 4 times several eV, okay? So you see, this is 1% times 1%. Okay, so that will give us microwave to far infrared range. So let me summarize. The three terms, this, not counting the quantum number, the characteristic energy scale, h bar omega, h bar over 2i, they have very different energy scale. The first one is several eV to 10 eV. The second one is 1% of the first term. The rotational one is 1% of the second term, thereby 10 to the minus 4 of the first term. This range, okay? Ultraviolet, infrared, far infrared to microwave. So that is the idea. You should remember one number for your thermal physics course. Room temperature is 1/40 eV or 0.025 or 0.224. That is more accurate, but if you have this, it's okay. Okay, 0.025 eV. So you know, room temperature means warm, a bit warm, right? 20 something degrees Celsius. So you compare this ballpark range with this, the vibrational one is in the infrared, warm, okay? So what is the picture then? The whole picture of drawing out this molecular levels. The first term refers to this minimum, but now we know there are more things to specify in order to totally indicate the molecule's energy. First thing, there are vibrational quantum number. And we know harmonic oscillator has evenly separated allowed energy. So look at this, n equals 0, n equals 1, n equals 2, n equals 3, okay? Now, you must realize, even so, we are only zooming in around here for the reason, if this is regarded as 1, well, we know that that is about 7 eV, 10 eV, things like that. If we got it as 1, all this level will be 1%. So this will be 0.01 eV, okay? Meaning there will be about 100 thing here on the proper scale, okay? Therefore, it's very difficult to draw it out in its completeness. But if we only focus on here, we already have a feel, okay? So this is the vibrational level. Do you follow me? But on top of it, we have this L times L plus 1 h bar square over 2i, all right? Therefore, even within the n equals 0 vibrational level, the energy becomes a constant plus the ground state energy for vibration. However, you still have this L times L plus 1 h bar square over 2i, okay? So look at this. The first term is this number, minimum. The second term referring to the ground state of the vibration, so I'm living here. But even so, we have to address what is L, okay? And we know that L, YLM theta phi, okay? L can be 0, so-called S state, P state, B state, etc. Okay? So now If you draw it out, L equals 0 will be 0, so it will be overlapping with this number. L equals 1, it will be 1 times 2, so it will be 2, that will be the first line here. If L is 2, it will be 6 times this value, so this will be the second line here, okay? The third line will be 2 times 3, that will be 6, that will be the third line, and so on. Okay, so do you understand why it is getting wider and wider here? Okay, all right. So now, this whole thing is associated with n equals 0. It shouldn't stop. There will be higher ones actually, okay? But that is not the whole story. What if I have n equals 1 vibrational level, okay? In that case, this term will start here. So therefore, I have this second series, and n equals 3, I have another series, okay? So this is brought up here. So that's part, if I take this, make it bigger, it will be something like that, okay? And then I have another series. So what does it mean? It means a molecule could take on such energy, and then you have to describe this energy by this number, n equals 0, and L may be equal 7 or 6 here, okay? So you have to write on the envelope the full address, including the electronic energy, which is the minimum, the vibrational level N and L, okay? That is the complete description of the energy of a molecule. Get me? So finally, just a remark that has to do with your thermal physics. There's a sample question this week also about this. Now, for those who know a little bit of thermal physics, I'm giving you this number so that you have some idea. The H bar omega is in this ballpark, okay? At room temperature, it is still quite difficult to thermal excite molecules to n equals 1 because they're comparable, only comparable, not big by much. However, thermal energy, this number, is much bigger than the rotational typical spacing. This is h bar squared over 2I. The meaning of which is thermal energy can populate the lowest vibrational state, but different rotational levels. The reason is that this, I think even up to here, okay, it is some number, a constant, it's not 0, some number, okay, h bar over 2I, and this is 0.001 UE, okay? And thermal energy KT is higher than that. So by Boltzmann factor, if you have learned statistical physics a bit, that is the most important result, exponential minus this energy divided by KT, then the molecules can be here, 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 here in a gas. All right, so you have some molecules low in energy, high in energy, distribute among this rotational state associated with the lowest vibrational state. That is usually the case. So the last page is just a summary of what we discussed, but also tell you the ballpark range. Okay, now this is physical sense. Now, the complication comes from there are so many descriptions. We have been using electron volt, but if you talk to different people, they will use different units. So you will see the Hertz. Okay, so this is up to 10 to the 11, and then this terahertz here is far infrared. Okay, and then somebody will talk about wavelength. Somebody will talk about wave number. Okay, and then some will talk about joule. And I told you what are the numbers in EV. Okay, so all in all, just take this take-home message. Microwave will be related to rotational motions. Far infrared also partly responsible for rotational motion because it is 0.001 to 0.0001 eV. So it's about this ballpark. Infrared will be related to vibrational motion of the molecule. And then ultraviolet and partly in the visible range will be electronic transitions. That is the atomic transitions, okay? So that is the big picture. So let's take a break now, and then we will develop these transitions. By that I mean, this here are the allowed values. What if a molecule start from here, go to there? What will we see? Okay, that is the question. Okay, that is related to the fact that you put a glass of cold water into the microwave, then later, 2 minutes later, it becomes warm or hot. Okay, don't do it for too long in your microwave oven. Okay, so let's take a break.